Hello everyone, welcome back to our channel. So today we are going to start with another topic from the CSES problem set, that is range queries. So we would be covering all the concepts that involves the solving of range queries, and we would be covering all the questions from start till end. I've solved these questions for now and would be posting the solutions for them. So let's start with the first problem, and we would be discussing two problems in today's video. First is the static range sum queries, then it would be dynamic range sum queries. So without wasting time, let's jump hop into the problem. So the problem is saying we are given with n integers and your task is to process q queries, and we have to find the sum of the values in range a to b. Okay, so we are given with the integers this and okay. So the first thing, so the problem is actually saying us, let's discuss what the problem is saying first. So the problem is saying, let's suppose we have given with this array and we are being given any range from a to b, and we have to find the sum of all the elements in this range. Let's suppose this is the array, so if let's take it as 1 based indexing. So if I say a has to be 1 and b has to be 3, so a1 to 3. So if we take this range, so I need to find the sum of these three elements, that would be 11. So this is what our problem is saying. So we are given with q queries and we have to find the solution to this. So first approach that obviously comes into our mind is the brute force approach. Like for each query I'll iterate from a to b and would find the sum, but that won't be a acceptable solution, as the complexity, in the worst case complexity, will go into O of q into n, which would end up in 10 raised to power 10, and that would give a TLE solution. So the next approach that we can think of is using the concept of prefix sums. Let's see what prefix sums means here. So if I'm given with an array A, and if I define P of I, which would be P of like P of I is that stores sum till ith index from 0 to I, from 0 to I, this is what it's saying. So if I need to find the sum from A to B, so I can simply say it would be prefix of B minus prefix of A minus 1, because this would give me the answer from 0 to B, and this would give me the answer from 0 to A minus 1. Subtracting the ranges would actually give me the sum from A to B. So prefix array would simply goes into prefix of I is prefix of I minus 1 plus A of I. So this is our prefix sum array, prefix sum, and the complexity would this be goes to O of q or O of n, whichever is larger. This will land up into this complexity. But uh, let's suppose, but this is an acceptable solution. Yeah, this solution would work. But what if I add a simple modification to this? Let's discuss a simple modification to this. What if I am given with an array a? Let's suppose a is my array, and like now I'm having two types of queries. For query type 1, you give me the answer for range a to b, like what is the sum in range a to b. But for query type 2, I will give you two parameters, one is k and one is u, which means that update the kth index to u. Alright, this means that let's suppose we have a 1, 2, 3, 4 and 5. So for first query, if I give 1, 2, 3, so this would find the sum from 2 to 3, and this would be 5. Now if I say query 2, change 2 to 6, so this would actually, so our array would something go like 1, 6, 3, 4 and 5. So this is how our array would be changed. Now if I say, and if I go to find the prefix, if I use the prefix logic, this would actually give me TLE, because on every update my array is being updated, and computing the prefix sum with an updated array would cost me O of n operation, and the worst case would land up to O of nq. So this would actually give me a TLE. Now, what could be the possible solution, like how we can actually optimize this to O of q or O of q log n? So actually these problems can be solved by two different solutions. One is the using of sparse table, and another is the use of segment trees. In today's video we will be discussing the segment trees portion, like how we will be solving the problem using segment trees, and this is the most widely used approach. So let's see what do we actually mean by a segment tree. So you can understand a segment tree, like from the tree actually we can understand that it would be having a root node, and then it would be having a children nodes, and we would be computing the solution for the children nodes, and then for this particular from this to this, and then finally for the solution to root. Like it simply means that we would be actually breaking down our exact like a bigger problem, into children subtasks. So let's understand what we say. So if I'm given with an array, A, and but if I say, let's suppose if I know the answer to, like if I know the sum for range 0 to mid, and also from mid to end, so I can say I would get the answer for this particular range from 0 to end by just adding the ranges for this particular two. Let's suppose this is x and this is y. So my answer for this would be x plus y. And similarly, I can say for this particular x, I can divide this into mid dash and this into two ranges, 0 comma mid dash, and for this it would be mid dash comma mid, and similarly for this mid comma mid double dash and mid double dash comma end. So if I know the sum for this particular two ranges, then I can compute the range answer for this range, and finally that answer can return be here. So this is how our and this would end up actually going till all the leaf nodes, and leaf nodes would be our array elements, a of 0, a of 1 till a of end. So this is how, like, we can see, like, okay, so let's understand how we are actually reducing this our logic. So if we say, so all the segments, now with this logic actually we have covered all the segments. Okay, so let me say, so we have covered the segment for single elements, that is the leaf node. With a layer above the leaf node, we have covered the segments with two particular nodes, considering two at a time. Then we are covering the elements with four at a time, right? So this is how we would be actually building a tree. And for every query, for A to B, if we need to find the range from A to B, we would be traversing all these segments starting from the root, and would be end up in three conditions. So this would end up in getting three conditions. So three conditions. So what are these three conditions are? Let's suppose we are dealing with all the ranges that we have in the tree, and this is our initial range that we are considering from A to B, and this is our start to it. If there is a partial overlap, if a partial overlap, we would recurse. We would simply recurse. We would say go to its children nodes and find me the answer. But if it's a complete overlap, complete overlap, in that case we would be adding the value of the tree. So let's suppose our tree, and we would be adding that node value, so returning that node value. So this would be returned. And if it's out of range, if it's out of bounds, we would simply return 0. So this is the three conditions while we use the query part. So when we will be giving a query, so this is the three conditions that we would be using. Now let's see the next part, the modification that we have discussed. Modification. What if what if we update element as well? So when we are updating the element, in the previous approach we have discussed that updating the element would lead to me getting the updation of complete array. So this would be give me a O of n time. But what if when I would be going to update the tree? So how would be actually going to update the tree? So in that particular case, let's suppose we have a range, this from start to end. We are talking about any range, and we are talking about the kth position. So we would be checking, if let's suppose this is the mid, we would be checking if that k actually lies in the left part of the tree or the right part of the tree. So if it lies on the left part of the tree, so we would be traversing the left part. If it's on the right part of the tree, we would be traversing the right part. And when our start is equal to end, that means we have actually reached this kth node. We actually read this kth node, which would be, and then we would be updating our tree node for that particular case to u. And when we would be backtracking it, we would be updating our tree node is equals to tree with the left child plus tree with the right child. I know you might be a little confused of how this is working. Let's see the code, and I guess you will get a better picture. So yeah, so this is the code that I have written for the segment trees. So let's understand how a segment tree is being made. So we have introduced a segment tree. The tree size would actually be 4 times of n, as we would be initializing the nodes as to be I. The nodes would be I twice of I plus 1. So this would end up getting a 4 times space complexity, and this is how we would be building the tree. So building the tree would be actually is, so we would start with a mid and traverse to the left side. So this is the left node, and this would be the right part of the node. And for every node, I would be updating that for every node, it would be, let's suppose we are talking about the root. We are at the root part, and we have divided into mid. So this would give me the left part, and I'm going to the right part. At the time of backtracking, I would be updating by this node. So this node is initially 1, which would be 1, and my left would be, I would be updating this with my left plus tree of right, because this is what my tree of that particular node would be storing, sum of left and sum of right. The sum till left plus the sum till right would give me the answer to this particular range. So this is how our tree is built. For every query, we have been given a start, end, and a range that is given to us, a comma b. So we have defined this to be l comma r. So if there is no overlap, we would be returning 0. If it's a complete overlap, like the start and end range, like the small portion of the range that we are considering is actually lying in that 8 comma b range. So we would be returning that tree node. And if it's a partial overlap, like uh, partial overlap as in we are talking about this range from start till end, and our actual range that we want from A to B is something like this. So this is a partial overlap, like not a complete range of this is in this A comma B. So we would be actually then further breaking down this start comma end into subparts. So we would be traversing that, and it would be left part and the right part, and then we would be returning the answer as to be left portion plus the right portion. And this is how we are taking the input a comma b, and for t equal to 1 we would be like for t equal to 2 it would be finding the range minimum. So this is the zero based indexing, converting to zero based indexing. Now here comes the update part, how we are updating the node. So we have found the mid element. If the position that we want to update is on the left side of the mid, so we need to actually go on the left side, like the left subtree. If it's on the right, we have to go on the right side of the tree. And when we have reached that particular node, so this would actually be when start is equals to end, we would be updating a tree node to u and would return that updated node, and would be backtracking our tree. So we would be backtracking our tree and updating the every node from that particular level to the topmost level. So this is how we are updating and backtracking and finally returning the tree node. Like we could return and we could not return. Like this is how we could make it. But yeah, we are not using that update. So it can be a void function as well. And for every query we are updating as well. And for the next part we are finding the min. So let's see if this solution get accepted. The static range we have discussed, like it would be simply just in the similar code, just remove this update part, and the code would work perfectly fine. Let's submit this code for the dynamic range sum queries, as dynamic is a like enhanced version for the static part, as you can understand from the naming only. So yeah, we have submitted, and the code is accepted. Yeah, so this, I hope you have got a bit of a sense of how the segment tree is actually working to find us the range of queries. In next solution, we would be discussing about the range XOR queries and the hotel query. Hotel query is actually a good question. We would be discussing that in the next problem. And the range minimum and the static minimum is actually the similar problem. Just in case of plus, you need to find the minimum. So it would be a small change, but I would recommend you to see and think and solve this problem. And if you have any questions, do let me know in the comment section. Would be solving your queries over there. So thank you.